We will now move towards one of the most simplest type of steel buildings, which are called industrial buildings. Buildings are constructed to alter the environment locally by enclosing space, and building structures give strength and stiffness to the enclosing elements. The simplest building in steel structure is a single enclosed space or a single space building. Most commonly, these buildings are used in industrial areas. If the function and behavior of a single space building is understood, then understanding building structure of more complex building is relatively straightforward. In the case of single space buildings, we can have many spaces such as factories, sport halls, theaters, churches, etc. The figure shown over here shows many such type of single space buildings. In this first, all these structures are examples of a rigid framed structures. We have a series of portal frames stacked behind each other. Thus, we can have a simple column and beam elements covering the space. The frames, which are essentially called portal frames, can be braced with each other as shown in this figure. The bracing, there can be one bay which is braced, or two end bays which are braced, or we can also have multiple bays which are braced. Instead of single beam and column arrangement, we can also have a lattice girder. Thus, the lattice girders can be stacked behind each other and braced, as in the case of portal frames. We can also have suspended portal frames, which again involves columns and beams arrangement, where we can have cables providing additional support. These cables are helpful in stabilizing the columns and also breaking the span of the beams. So all these four structures are examples of rigid frame structures. Beside rigid, we can have examples of simple beam and column sections where we don't use any portal connection. We just have simple pin connections joining beams and columns. In the case of simple beams and columns arrangement, we have to introduce additional bracing to stabilize the whole structure. The shape of single spaces can also be cubic, spherical, or any defined organic geometry. However, the majority of new buildings are rectilinear for a number of practical reasons, so the basic structure is the structure for a cubic single space. The explanation for the behavior of the structure for this single space uses six basic concepts, which are as follows. The first one is the function of a structure is to transfer loads. The second one is the load path is the structure for each load. The third point related to the structural behavior is the structure transfers load by forces in the structure. The fourth point is forces in the structure can be considered to be a combination of direct and shear forces and bending moments. The fifth point is the structure must have overall stability. And finally, the collapse initiated by slender structure must be avoided. The application of these basic concepts give an understanding of a structural behavior, and also it provides a basis for a more difficult process of structural design. The design process is more difficult than understanding the behavior of existing structures as concepts, because the design uses the concepts simultaneously, and that is more challenging. Now let us dig deeper into a single space steel structures and use these six essential concepts to fully understand their behavior. It is important to keep in mind that these six concepts apply to the whole structure and they must be applied to every part of the structure, from each bolt or weld to the whole structure. So, in our discussion, we will keep the shape of the building as rectangular with a simple pitched roof. We shall now discuss these six concepts in the context of single space steel structural buildings. In the case of multi-story buildings, we introduced these four variables for distinguishing one structural form from another. These four variables are also applicable to single space buildings. In the case of industrial buildings, single space structures can be industrial buildings or sheds, warehouses, halls, etc. Industrial buildings are generally designed as enclosures that provide functional spaces for internal activities, which may involve the use of overhead cranes or suspended equipment, as well as it might require provision of office spaces or mezzanine floors. Various structure forms have been developed in the last 40 years that optimize the cost of steel structure in relation to the space provided. Some of these forms were introduced earlier. The most elementary system used for an industrial building consists of a column and a beam. This configuration can be modified in numerous ways using various types of connection between the beams and columns and for the column bases. The types of structures most commonly used in industrial buildings are portal frames with hinged column bases. Portal frames provide sufficient in-plane stability and thus only require bracings for out-of-plane stability. Some arrangement of beams and columns are shown in this figure. The first one is a simple beam and column frame. This frame is unstable in plane, hence it would require some bracing for stability. The advantage of this frame is that there are no negative moments appearing at the extreme end of the beam. The second frame is a portal frame, which, as we said, is the most common option for industrial building. In the portal frame, we have negative moments appearing at the top hinge and at the column top. In the third case, we have a simply supported truss instead of a single beam. This simply supported truss can cater for large spans. However, similar to our first example of simple beam, this truss system is also unstable in plane of the frame. Hence, it requires some stability measures. In this fourth option, we have a portal truss. In this portal truss, we have moments appearing at the end of the truss, which gives an in-plane stability to this system. This portal truss system is similar to the portal frame, which have got moments appearing at the end of these inclined beams, or also called rafters, and because of these negative moments, the frame becomes stable in plane. Some common terminology used in the case of single space steel structure is shown in this figure. This is a figure of a portal frame, which is made up of columns and the inclined beams called rafters. The top or the highest point of the portal frame is called apex, whereas the ends of the rafter which are meeting the columns are called eaves. As we discussed, the apex and the elves have got negative moments. In order to provide a robust connection at the location of negative moments, we can have these locations reinforced by haunches. These haunches stiffens up the apex and the elves and gives a robust moment connection. In this figure, we have variety of rigid frames with a fixed or a hinged column bases. The fixed column bases may be considered when heavy cranes are used as they deflect less under horizontal forces. On the other hand, the hinge column bases have smaller foundations and simple base. All the types of single frames discussed over here can be stacked behind each other, giving us a single story industrial building. In the first four figures of these pictures, we have rigid frame structures. In the case of rigid frame structures, two examples were shown earlier in these structure concepts. The example of portal frame and a portal truss can be an option of rigid frame structures. In the last four figures, we have the single frame structure concepts. And the single frame structure concepts are the frame 1 and frame 3, which is the simple beam frame and the truss frame. In this option D of the rigid frame structure, the structure is located partly outside the building. So the details concerning the piercing of building envelope have to be designed carefully. This type of structure is called a suspended structure. By using suspended structures, which is shown clearly in this adjacent picture, long span building with high visual and architectural quality can be realized. The division into members that are predominantly subject to either tension or compression permits the design of lightweight structure. The suspended structure can be designed by extending the column outside the building envelope, as illustrated in this picture. Suspended structure accomplish long spans, although the suspension cables or the rods also penetrate the building envelope and can be obstructive to the use of external space. In the sketch D of this picture, involving columns and beams of simple frames, we have a cable suspended beam with purlins. In the frame of this structure, we have a long span beam which is broken by a cable structure. So this bold dark line shows a beam and underneath it is a suspended cable. And the vertical members separating the beam from the suspended cables are actually meant to break the span of this beam. In this way, we can attain long spans without providing intermediate supports. In order to cover a single space with portal frames, we can arrange the portal frame in series behind each other at some distance center to center. After that, all the portal frames can be connected by horizontal members shown in this figure. As we can see that in plane of the frame, the structure is stable. However, out of plane, the structure might not be stable. In order to ensure out of plane stability of this system, we can provide a truss system at either one bay or multiple bay, which can bring the lateral load applied in out of plane to these portal frames down to the ground. Now in this figure, we have a braced truss provided at the roof and vertical trusses provided at the walls. In case of lateral load applied out of plane to the portal frame will be attracted by this stiffer bay. The lateral load will be transferred to this stiffer bay roof, and from this horizontal bay it will transfer it down to the ground via the vertical truss system or vertical braces. The same is true if we opt for a lattice girder. In all these systems, we have either a bracing system at one bay or we have two bay braced for transferring the out of plane lateral load down to the ground. If we opt for a fixed connection at the base, then we can reduce the number of braced bay. However, in the case of pin connection, we might have to increase the number of braced bays. The same is true for the suspended portal frames. We can have cables provided to break the span of the horizontal truss. Please note that there can be a moment induced in the vertical member supporting the horizontal truss. In this case also, we have provided two braced bays. In the case of simple frame systems, we don't have stability either in plane of the frame or out of plane. Hence, in addition to the out of plane brace system, we have to provide in plane bracing system. As we can see in this structure system, we have provided a braced bay in the in plane direction to take the lateral load down to the ground, and also a braced bay in out of plane direction to bring the load down to the ground. Similarly, we can have multiple braced bays and also bays braced in the in plane direction. It is noteworthy that only the bays which are at the boundaries are braced in the in plane direction of the simple frame. In the case of truss structures, we can also have braced bays in the plane of the truss frames, and the braced bays are provided at the boundaries of the structure. The type of frames discussed in this picture can be all called as a distinct forms of a single space steel structures. As we discussed in the case of our multi-story buildings, that there are four variables which distinguish one form from another. These four variables encapsulate the six concepts which we discussed earlier. Thus, the function of structure to transfer loads, the load path, the structure transferring loads by forces in the structure, and forces in the structure can be considered combination of direct shear and bending moments, are all the features of functional framing. Whereas the concept 5 and 6 involving the structure overall stability and the structure local stability are covered by the stability system. We can distinguish the construction technique of all these systems. We can also distinguish all these structure forms in terms of construction techniques. Like for example, the construction of normally single story, single space steel structure involves first of all construction of a braced bay, and using that braced bay as a stable box, one can stack series of other bays behind and in front of it. We can have either the construction starting from the brace bay located in the middle, or we can construct two brace bays at the end and then make our way towards the center. Similarly, we can have different foundation systems provided to these structural forms. Thus, the main takeaway from the discussion so far about the single space steel structural systems is that we can either have a pinned frame system, which can be unstable in plane and out of plane. This pinned system can be stabilized by providing a truss system shown over here, which transfers the lateral load in plane of the frame to the ground, and also a truss system provided as shown over here, which transfers the out of plane loading to the ground. In another option, we can have a total frames stacked behind each other. In this system, the lateral load in plane to the frames will be automatically transferred to the ground by the moment connections or by the total action of the frame. Whereas for the out of plane lateral loading, we have to provide a trussed bay. Hence, in case of total frame, we need only transverse truss system. Whereas in the case of pinned frame structures, we need transverse truss system as well as the longitudinal truss system. These two types of structure form can be classed as distinct based on functional framing and stability system. It is important to appreciate that these 6 concepts must be applied to every part of the structure, from each weld or bolt to the whole structure. In our further discussion, we will apply these 6 concepts to the basic rectangular shape of the building having simple pitched roof. The building is shown in this figure. We can see that the building has a roof covered with some cladding. The cross-section of this building is shown in an adjacent picture. This building has a roof covered with a corrugated metal sheeting and the walls covered with brickwork. The main structure is a portal frame made up of steel. The floor is of precast concrete and the foundations are in situ concrete. This type of building is used widely throughout the world for factories and warehouses. To begin with, we have to understand what the loads are. The sources of the loads will be gravity, lateral load, which can be wind or seismic. The gravity will apply vertical loads. So in the case of gravity, we can have the weight of the roof, weight of snow, weight of walls, floors, and other items contributing to gravity. Wind or seismic load will apply at right angles to the roof and walls. In this picture, we have taken wind load. We can see that the wind load can cause an uplift force on the roof depending on the slope angle of the roof. We have to understand that the space is three-dimensional and the structure is also three-dimensional. However, each element is either one or two-dimensional and will act as a one-dimensional or two-dimensional structure. For this structure, the elements can be identified as one or two-dimensional. Like for example, roof sheeting in reality is a two-dimensional structure, but they act as a one-dimensional structure. The masonry wall is a two-dimensional structure and their action is also two-dimensional. The steel frame is a one-dimensional structure and their action is also one-dimensional. Precast flooring is a two-dimensional structure and their action is one-dimensional. Similarly, foundation is one-dimensional and their action can either be one-dimensional or a two-dimensional depending whether we have lateral forces also considered within the foundation. In order to further understand these, the type of the structures and the actions induced by these elements or structures, let us discuss each and every component independently. This will help us to identify load path and assess the structure behavior of each and every element. So let us discuss the roof sheeting. The roof systems serve as the building envelope and provide stability for the main support structure. There are number of proprietary types of claddings that may be used in industrial buildings. Now we will discuss common systems for roofing and cladding that serve as the building envelope and may at the same time provide stability for the main support structure. There are a number of proprietary types of cladding that may be used in industrial buildings. One of the example of most common type of cladding is a single skin trapezoidal sheeting. This type of sheeting is widely used in agriculture and industrial structures where no insulation is required. This type of sheeting is good for roof slopes up to 4 degrees. The sheeting is fixed directly to the purlins and side rails and provide positive restraint. In some cases, insulation might also be provided. We can also have a double skin or a built-up roof systems which are used with steel liner tray that is fastened to the purlin. The liner tray is followed by a spacing system, insulation, and outer sheeting. Because the connection between the outer and the inner sheets may not be sufficiently stiff, the liner tray and fixings must be chosen so that they provide level of restraint to the purlins. Similarly, we can have many more types of cladding systems. The roof cladding system is a 2D structure as we can see in these two examples. However, the load which they transfer to the purlins and from there onwards to the hot rolled rafter is of one dimensional. Now let us discuss the wall systems. Similar to the roof cladding, numerous wall systems exist for the design of external walls for industrial buildings. Cladding types made up of steel sheeting are most frequently used. In the case of wall cladding system, we can have hot rolled column connected to a cladding rail and the cladding rail joined to a cladding system. In this figure, we can see that we have two sheeting with a insulation sandwiched in between. The cladding rail can be of a cold form steel similar to a purlin used in the roof system. Instead of steel sheeting, we can also use masonry wall as a cladding system. The wall is connected vertically for vertical loads and is connected laterally for the lateral loads. Masonry wall is a 2D structure and hence its action is also 2D. We can see that the masonry wall transfers vertical load in one direction and the lateral load in the orthogonal direction. Hence, the actions induced by the masonry wall are 2D. The next element is the steel frame. We discussed previously that the steel frame is made up of hot rolled columns and hot rolled rafters connected to the column via fixed connection. The rafters are also connected to each other by a fixed connection. Instead of portalized frame, we can also have trussed frame arrangements as shown over here. In the case of portal frame system, we can have different parts such as the wind bracing, the roof bracing, and the gable posts. Thus, the steel frame is a 1D structure because the frame is stretched in one dimension and its action is also 1D because the loads are applied in the same direction as the plane of the frame. Next element is the precast concrete floor. The precast concrete floor units are two-dimensional. However, they span in one direction and hence their action is also limited to one dimension. Therefore, the precast floors in this table is shown as a two-dimensional type. However, their actions are one-dimensional. Finally, we have the foundations, which are one-dimensional elements, but their structural action can be either in one dimension or in two dimension, depending whether they are transferring gravity loads or both gravity and lateral loads. We shall now discuss how the gravity and the lateral loads are transferred to the foundation. Maximum vertical load will include weight of each and every element because all elements have self-weight due to gravity. In the case of building, this self-weight, which is in vertical direction, comes down to the ground. On the roof of the structure, we can have snow load or load due to rainwater. That load can also contribute to the vertical load. So, snow plus the sheeting load will be transferred to the longitudinal purlins. And from these purlins, the load will be distributed among the portal frames. Thus, in this figure, we have the load from the sheeting getting transferred to the purlins. The purlins are stretched longitudinally. From the purlins, the load gets transferred to the portal frames as shown in this figure. Portal frame will also have its self-weight, which is shown distributed over here. All these vertical loads, including the weight of the sheeting, snow or rain, self-weight of the purlins, and then the self-weight of the portals will be transferred down to the ground. The foundations will be loaded by the reactions to the portal frame plus the reaction of the self-weight of the walls and also the reaction to the floor units. We can realize that the load of the walls and the floor units are directly transferred to the foundations, although apparently the masonry wall might seem connected to the portal frames. But the connections are just to ensure stability. They are not meant for transferring the loads to the frame. Now we will discuss the transfer of lateral loads. As we said, that the lateral loads are normally transferred in orthogonal directions. The lateral load are carried by the roof sheeting and the wall claddings. The lateral load is transferred to the portal frames via the roof and the wall systems. If we consider wind load as a lateral load applied to the structure, we will have load developing at the roof sheeting and the side walls, and these loads will be directly transferred to the portal frames. In this figure, we have a suction load or wind uplift induced by the sheeting, and that load is shown with arrows pointing outwardly. Due to the side walls, we have reaction from the portals, and that load is shown in the direction of the wind load. Thus, we can say that the loads on the intermediate portals are due to the reaction of the purlins and the sidewalls. These loads due to wind can be added to the self-weight of the structure. And finally, we will get the overall load on the portal frame. Therefore, if the lateral load is in the transverse direction of this 3D building system, that will be distributed among the portal frame after being transmitted by the roof sheeting and the side walls. However, if the load is in the longitudinal direction, the gable frames help to transfer the loads to the braced bay, and the brace bay correspondingly bring the load down to the ground. The brace bay at the roof level is normally called wind bracing. In this picture, the wind girder and the elevation wall brace system is shown. We can see that the brace bay is the stiffest bay of the whole system. Hence, it will attract most of the load, and that load will be transferred via truss system from the wind girder to the wall brace system and finally to the ground.